Hi and welcome back to Module 6, and we're looking today at titration curves as part of our inquiry question 3. So we've done some titrations now in class, and we've looked at finding that point with the indicator where the colour is just changing from one of our indicative colours to the other, and that's what we're calling our end point. So when we actually see that colour change occur, we're looking at the end point. Now hopefully the end point is fairly close to the equivalence point, which is where those OH ions are equal to the H plus ions. But another way we can see this is in our graph, and we can call them titration curves, sometimes a pH curve. And what this is doing is this shape of the curve is sort of giving us a little bit of an indication of what's going on in the reaction, and it does depend on the different types of acids and bases that we have in the reaction. Now sometimes these are really good to use because if we are titrating with a solution that has a colour, for example our Coke or our red wine or whatever, and we're trying to work out the acid content in that, it makes it quite difficult because an indicator is not going to show an obvious change there. So sometimes we can actually use a pH meter like we have been using with the data loggers, and just actually recording the pH then, and then we can graph it. So here we have an example of a strong acid with a strong base. So what you can see here is we are starting off with a strong base, and you can tell that because it is up in the high pH range. We can have a similar graph that would just be flicked around if it was our strong acid, strong base with a strong acid, starting off with the acid solution in the flask and adding the base to it. So it would just be the mirror image. But what we're seeing happen here is we're starting off with a base solution, and in our burette is our acid, and we are adding acid to that base solution. So what's happening is as we're adding acid to that solution, it's still got an excessive amounts of the hydroxide, which is why it's sort of only slightly changing as hydrogen ions come in and sort of neutralizing and forming water. We can see that it's a gradual decrease, and it remains fairly constant until we get kind of fairly close to the equivalence point when it suddenly drops. So you can see here it's dropping from about 10 or 11 straight down to a 2 or a 3, and what we're seeing is that now the acid or the hydrogen ions are in excess, and the more we add, it's gradually changing but not a significant amount. But we can use this curve to work out where our equivalence point is, and our equivalence point is at the midpoint of where we see that sudden change or drop. So if we have a look at another graph, we can see here we now have a strong base, so we're still up high in that pH range, but we're adding it with a weak acid. So again, I'm adding more and more acid to that solution, and you can see here even the gap from here across to here, and our volume of acid added is about 25 mils, and you can see there that more of that acid is required to neutralize that base. So again, you can see it's only a fairly slight decrease there in our pH as I'm adding just a weak acid to that solution. But again, once it reaches this point, it can be just a number of drops that cause that pH to drop, and you see here it suddenly drops into almost a straight line. So we can notice then that the pH drops off again, and near that, just after that equivalence point, it flattens out again, and adding any more of that weak acid isn't going to change our pH down to the 1 zone because it's a weak acid, so it doesn't dissociate quite so much, so it's not going to end up in that area anyway. So let's look at another one, and now we have a weak base with a strong acid. So you can see already that our weak base is in a stronger pH again because it's a weak base and it doesn't fully dissociate there. So we're starting off at about that 10 or 11 mark, and so the pH is sitting in that basic region. Now as I'm adding some strong acid to it, it is again decreasing slowly, as the base initially is still in excess, but once I reach that point, we get a sudden drop, and all of a sudden our hydrogen ions are then in excess. And again, you can see here that it levels off again at the base after the at this basic, well, the base point down the bottom. It flattens out again, and again we now have hydrogen ions in concentration, and again, depending on what acid it is, it's sitting at about a 1 pH, which is where you would expect a strong acid to be. Now here you can see a weak acid with a weak base, and you can see that the shape of the graph is quite different to the other three graphs that we've had a look at. And the main reason for that is a weak acid with a weak base. It's starting in that basic region. We're adding the weak acid. You can see that it's dropping off a little bit steeper than it has with any of the other graphs, but still dropping off a little bit. But there's no real clear change in pH at that equivalence point. We're not getting that sudden drop that we were getting with the other two. And due to this, we don't tend to actually perform these in a titration. If anything, they would be completed with an automated titration rather than a manual one, because it is so difficult to determine. So in class, what we're going to do is we're going to have a look at some of these graphs and use those graphs again to continue our volumetric analysis that we have been performing in class, but this time using our graphs to help us with that. So I'll see you.